Thank you for joining us for this webinar on what's new in the HyperLynx VX.2.4 release. We will begin by covering power-aware design, beginning with a description of what is and why it is important. We will explain the process of model extraction for power-aware analysis, and then how it can be simulated in the new HyperLynx VX.2.4 release. We will continue with a discussion of the SerDes Wizard that was introduced in HyperLynx VX.2.3, and the continuing development in the current release with AMI model support, additional protocols, and the new JCOM engine. Following that, we will then talk about multi-board support and DC drop analysis, and finish with new design rules that have been added to HyperLynx DRC, emphasizing the new 3D or multi-layer creepage rule. This rule uses the new 3D creepage algorithm that engineering spent a significant time developing. New in HyperLynx DRC VX.2.4 are not only these DRCs, but also two new out-of-the-box rule group folders, one for analog and one for safety. Let's start with power-aware design. Power-aware analysis is the co-simulation in the time domain of high-speed signals together with the effect of the power distribution network effects that we need to incorporate into this analysis. The first one is the simultaneous switching output effects, which cause voltage droop in the voltage rail. There is also the via-to-via coupling through the PCB power cavity and return path discontinuities associated with the high-speed traces. The first two effects are the most prominent ones, so we will focus on them. Let's define the terms further. SSO, or simultaneous switching output, occurs when multiple drivers switch at the same time, resulting in a temporary high current demand on the I/O voltage rail. And SSN, or simultaneous switching noise, is the voltage disturbance on the driver's I/O rail that occurs as a result. In this picture, you can see the top green waveform is for the 1.2 volt power rail for DDR4 with 1-bit switching. It's difficult to see under the green line, but there are also some orange lines showing a little more noise with 8-bit switching. But with 64-bit switching, the red trace is showing a significant effect. The voltage drop at the controller is affecting the DQ signal at the DRAM in the lower window. Another effect that we need to incorporate into the power-aware simulation is via-to-via coupling to the PDN. When a signal transitions through a via, it can excite the power cavity, and then when there are nearby vias, they can couple to each other when they are sharing the same return path. This kind of noise is a bigger issue for single-ended signals such as are found in DDR4 designs. In this picture here, which is extracted from the board, you can see the via crosstalk effect as you get the higher frequencies. So what are the models that are needed for power-aware simulations in HyperLynx? The IBIS model needs to be power-aware and have sections for pin mapping, ISO, PD, and PU models, composite current, a package model or SPICE S parameter package model, and on-die decoupling models. Additionally, we will need a PDN model of the power pins to account for the non-ideal PDN effects on the PCB. And then the via-to-via coupling model as well to account for the via power cavity noise. How do we create the PDN models at the power pins? We now have a new dialog box you can invoke by selecting Manage Power-Aware SI Models under Analyze 3D EM. To create this model, you will need the PI bundle. Then, when you select this and create the model, the Advanced Decoupling Wizard will open and you will go through the steps, and then you can simulate to create the actual models. Then you will need to create the via-to-via coupling model as well. From the same dialog box, select the nets and the vias, and all the vias will be automatically selected. Select for signal via-to-via coupling, and the PDN model extractor will run the analysis and create the models. There is another way to create these models. The hybrid solver includes via-to-via coupling as well as signal trace effects and models the non-ideal return path. It has the ability to create a model with both the signal and power pins together. Currently, this runs separately in the hybrid solver, but in the future, it will be incorporated into the wizard. Once the simulation completes, the created models will be listed. You can see here the PDN model and the via-to-via model are selected. To isolate the effects of either, you could select only one model at a time. Select the PI effects button on the toolbar. If include power bus coupling is selected in the PI effects settings window, all nets related to the power net will be selected, which is needed to simulate SSN. This needs to be turned on for more accurate simulation results, but the simulation time will be much longer. Once the simulation completes, the created models will be listed. You can see here the PDN model and the via-to-via model are selected. To isolate the effects of either, you could select only one model at a time. Select the PI effects button on the toolbar. If include bus coupling is selected in the PI effects 7, all nets. You can also simulate interactively or in the DDR Wizard. For interactive simulation, use the Easy Wave display so the power probe can be displayed. With the DDR Wizard, there are now two options. When crosstalk effects are enabled, you can include the via-to-via coupling by setting crosstalk to include S-parameter coupling. Let's show a quick demonstration of this new capability in HyperLynx VX.2.4. You can increase the accuracy of signal integrity simulations by modeling the effects of non-ideal power distribution networks and signal-to-signal via coupling through the power distribution network with a power-aware ISI interconnect model combined with power-aware IBIS models. Including these models in the simulation also helps to isolate noise coupling issues and better understand the source of noise in your design. A power-aware SI interconnect model is an S-parameter model that the software creates with port mapping information with respect to the IC power pins and all signal vias. The software enables you to automatically connect the model to the IC pins or vias using the port mapping information on the board design. You can see here they're running the simulations. So what this has created is models for the signal vias in the power distribution network. As you can see here, the two models are available to be selected and included in your simulation results. As you can see here, you can include one more model per simulation. You can include more than one model in the simulation. For example, you can include one that describes the power distribution and one that describes the via-to-via coupling. To see the effect of using power-aware IBIS models, look at the waveform of the two simulations, one with power-aware models and one without. The one on the left considers the effect of a non-ideal power distribution network, and you can see the effects in the noise created on the signals. This, in turn, affects the signal quality. With HyperLynx VX.2.4, you are now equipped to simulate your designs with more accuracy. Let's now go on to SerDes and protocol compliant design. Unlike double data rate or DDR technologies, which evolved over an extended period, SerDes technologies have evolved very quickly. There are only a few DDR specifications, but there are over 130 SerDes specifications, with speeds approximately doubling with each new generation. Most hardware engineers understand timing, have designed DDR interfaces before, and know how to make setup and hold margin measurements. But SerDes is a new ballgame. With the increase in data rates, there is also a shift to the type of analysis from eye diagram and loss evaluation at the lower speeds to channel-based methods at the higher speeds. Channel operating methods simulate quickly and do not rely on vendor-provided buffer models. They allow one to make trade-offs among loss, reflections, crosstalk, and device specifications. The hardware engineer faces multiple industry-related challenges when designing SerDes interfaces. First, SerDes specifications are increasingly complex to understand. Specifications such as those for PCI Express Generation 4 are over 1,000 pages long, which hardware engineers do not have the time to study. Training to understand protocol specifications can be hard to obtain and is not freely available. The typical high-speed design contains multiple SerDes protocols, which hardware engineers have to learn about and analyze from scratch for each new protocol. Second, AMI buffer models, which are typically used for greater than 5 gigabit per second channels, are not easily available. Further, the buffer models are written for EDA specifications that are not ratified by the IBIS committee, so they generate different simulation results in different EDA tools. Which one is correct? Finally, SerDes channel analysis and design requires electromagnetic expertise. Some design teams do not have SI or EM experts in-house, so the additional burden of generating S-parameter models that accurately represent the PCB design is borne by the hardware design engineer. With a HyperLynx SerDes Wizard introduced in VX.2.4, the hardware design engineer has access to the industry's first end-to-end SerDes interface compliance solution. The expertise needed to evaluate a channel's adherence to protocols such as PCI Express, Ethernet, USB 3.1, etc., is built into the tool itself. When IBIS models are not available, the user can use protocol-compliant buffer and package models to validate the interconnect from end to end. Advanced eye analysis in SerDes Wizard. With the release of VX.2.4, IBIS-AMI models are now supported in the SerDes Wizard to be used when they are available. Note that all selected channels must have IBIS-AMI models assigned to activate this option. And continuing the development of the SerDes Wizard, the VX.2.4 protocol support has been expanded to include 5G-based CR, and PCIe has been expanded with the addition of PCIe Gen 1, 2, and 5. HyperLynx now includes another compliance methodology called JCOM, which was created by JEDEC. To learn more about this, you can click on Christian Phillips' blog post link in the presentation. There are 3 categories in the specification, and HyperLynx currently supports the CS or C short class, but plans to support the other categories in the future. HyperLynx now also supports effective return loss, or ERL, which is a new metric for SerDes channel or package characterization. This accounts for the effect of RF receiver DSE and is a more accurate metric compared to the traditional return loss. Again, there's a white paper that describes more about this new metric. PAM4 eye density plots are now supported in VX.2.4. It used to be displayed as a consolidated eye, but now is shown as a PAM4 eye, as you can see here. There have also been improvements to the DC drop functionality in HyperLynx Power Integrity. HyperLynx DC drop analysis now supports multi-board configuration. The setup is the same as for a single board. In this example, we have 2 boards, and the results for each board are displayed in separate tabs. An extension of the multi-board support in HyperLynx VX.2.4 also supports DC drop analysis for rigid flex design. Again, the setup is the same as for any DC drop analysis. You can see in this example the results of the rigid flex simulation. Another feature was added for DC drop where you can now simulate multiple power nets with a combined ground return. This is useful for ensuring that the ground plane is sufficient to support the combined currents of all power nets. Moving on, we'll cover some high updates in the VX.2.4 release of HyperLynx DRC. HyperLynx DRC is a separate program that is becoming more important as an alternative analysis tool. There are some items that can be simulated, such as the signal integrity and power integrity simulations we have covered in this webinar. There are other effects that are more difficult to simulate, such as electromagnetic interference. This is where the HyperLynx DRC can be helpful. For example, now let's look at a subset of the requirements that you might have on your next design. Suppose you know that you will need to meet signal quality requirements for overshoot, ringback, and monotonicity, and the timing on your DDR and other interfaces needs to be checked. You also have to look at the power distribution network for current density and decoupling, and you have thermal issues you need to consider. Simulation of all these issues would be time-consuming. There are also high-speed serial links on the board that have to perform at a certain level, and many EMI and crosstalk problems that need to be checked. How will you address all these requirements so that you can sign off on a board with confidence? Manual inspection may be part of your design rule process, used to identify and eliminate structures that can cause EMI issues or other aspects of the design. This time-consuming process can be greatly reduced if this inspection can be automated. This can be done with the rules-based approach found in the geometric analysis engine in HyperLynx DRC. What are some of the enhancements in HyperLynx DRC and VX.2.4? New in this release is a stack-up editor similar to the one you are familiar with in other HyperLynx and Expedition tools. Also, based on feedback from the field, there have been some productivity improvements as well. For example, automatic net voltage assignments based on net naming conventions have been added. Note, not all customers name their nets in the same way, so this is custom configurable in the setup options window. Another improvement for usability, we can apply rules to more than one just the object list. In the past, HyperLynx DRC would default to running a rule on the entire design, and then you would have to use the pull-downs to target an object list. Now you can target directly all the net classes and constraint classes and everything in this list, all the data lists that are read in automatically. This allows the user to get up and running more quickly. HyperLynx VX.2.4 continues to add new rules making use of its geometric analysis engine. Added rules include analog rules for net under component, component isolation, and sensor net isolation. In the signal integrity area, 4 new rules have been added for trace shielding, routing layer, group-to-group spacing, and AC coupling capacitor value. New power integrity rules include PDN isolation and grounding layer, and another shielding rule under the EMI category was added. Creepage rules were added and enhanced to perform distance calculations on any layer of the PCB. To save research time, additional IEC international standards and charts were also integrated into the tool. As mentioned earlier, VX.2.4 added 2 new rule groups, an analog folder with the 3 new analog rules, as well as the new safety folder, which has the creepage rules. Here is the setup window for the new multi-layer rules for creepage and clearance. In the VX.2.3 release, we had a 2D creepage rule, which has now been renamed the same layer creepage rule because the rule was just an object-to-object check on the same layer. Now with this multi-layer or outer layer creepage rule, we have the ability to view the top and bottom layers of the board and have more extensive coverage when automating these creepage checks. These new multi-layer creepage checks take into account the board edge and also consider through the via or through a hole. So we're expanding beyond those same layer checks, measuring the creepage distance, the minimum distance required that objects be placed in order for there not to be a safety violation. We have 2 versions of the rule. Similar to the bare-bones creepage distance check, considering the multi-layer outer layers of the board will check automatically for high voltage objects or high voltage that have the ability to affect or radiate energy to what we call a victim object or victim net. In the second version of the rule, following the same idea with the 2D same layer rules, we also have incorporated creepage distance checks, but have embedded the IEC standards into the rule. So this is where we're saving the customers a maximum amount of time by embedding the charts standards that they have to follow for their guidelines into the rule. This removes a lot of tediousness of manually checking for creepage. These standards are regulations that companies need to follow depending on the environment that the PCB will be in. So for example, mil-aero or medical device companies with high voltage PCBs have to follow these ISE standards. With these checks, Mentor is the only company on the market providing an automated solution for this layout validation. Here is a short demonstration of these new safety feature rules and checks in the HyperLynx DRC VX.2.4 release. High voltage creepage checks are currently calculated by visual inspection, and it's a very tedious manual process to validate a PCB for this issue. HyperLynx DRC automates this process and expands it with its new multi-layer creepage rule and multi-layer creepage for safety standards. These new additions checks for multiple layers in the PCB in addition to the already existing same layer PCB checks. These DRCs have the built-in IEC standards, ensuring that the proper guidelines are followed and all criteria are met performing these checks. Similar to other DRCs, HyperLynx makes it easy to spot these violations. These electrical checks help to ensure a first-time pass for PCB validation. You can see in these examples the results of these checks. So these multi-layer creepage checks really expand the technology in HyperLynx. I would like to emphasize the value of these rules, and this goes for all HyperLynx DRCs. They provide a very efficient and effective method to perform layout design reviews. They remove the human error elements by automating the very time-consuming visual inspections that our customers have to do. And when you take into account the electrical perspective these DRCs provide, they are not just basic DRCs. They have the ability to assign IBIS models and take into account other electrical factors. Here, in the case of the electric static discharge high voltage safety element in creepage checks, for example. So with these rules, we're actually saving our customer hours or even days of effort. In the case of the creepage checks going net by net and using visual inspection to find these susceptible objects or susceptible net, and plugging in the value from the chart into the formula, this can take our customers weeks to do it. This is a very valuable streamlining of the release process. Thank you all for taking the time to watch this webinar.